Okay, so in this video, I'm going to give a little bit of an overview of the rate of a chemical reaction lab. So when you go into Canvas and have a look at the assignment, you'll see that you're asked to read a document that describes a particular experiment, and we'll have a look at that in a moment. I recommend downloading that to your actual computer so you've got the data handy. And then you're going to use the data that's contained in that document to answer a series of questions, and it's your answers to these questions that you will scan and upload to Canvas as a PDF. So there's a rubric underneath. You do get 1.4 sort of like just general formatting, and then there are a series of 7 questions, and it kind of gives you a few little prompts there about what you might want to make sure you've got for every question. Okay, so that's pretty standard kind of stuff. So let's have a look at the first document where we're going to get an overview and also our experimental data. So it begins by talking about chemical reactions and rate laws. And the first thing they talk about is that every chemical reaction will occur according to a specific rate that is described by a rate law. So a rate law expresses how the rate of a chemical reaction is dependent upon the concentrations of the reactants. And so what we see in a rate law is that we have a rate constant that is independent of everything other than the temperature. So it's characteristic of a particular chemical reaction, and it's only dependent on the temperature. And then we have the concentration of each reactant that is raised to a particular power, and that power is referred to as the reaction order for that reactant. And basically, the bigger the reaction order, the more sensitive the reaction rate is to the presence of that particular reactant. So if it's like 0 order in a reactant, it's not sensitive at all to the presence of that reactant. But if it's like 5th order or something like that, very high order, then it's highly sensitive to the presence of that reactant. Now, so that's the general kind of layout of things. And so what we're often wanting to do in a kinetic study is to determine what this rate law is, to figure out what the reaction orders are, and also to figure out what the rate constant is. Now, generally, there are 2 ways of doing this. One is more kind of generally applicable than the other, but it's a little more complicated. So the first method of doing this is what's called the method of initial rates. And in the method of initial rates, what you do is you do a series of experiments. And in your first experiment, you're going to keep everything constant, or in your first 2 experiments, you're going to keep everything constant, but you'll vary the concentration of one reactant. And then you'll do another 2 experiments where you keep everything constant, but you vary the concentration of another reactant. And so in that way, you are able to measure the sensitivity of the reaction rate to the concentration of each of your reactants, right? And what you can do is you can take that data and use this little expression here and get the reaction order for every reactant. So say you've got 2 experiments, 1 and 2, where you're varying the concentration of reactant A, but keeping everything else constant. What you'll do is, you do 1 experiment with a certain concentration of A, we're going to call that 1, measure its rate. That'll be your rate 1 and concentration 1 for A. And then you'll do another experiment where you change the concentration of A, but keep everything else constant. That'll be your experiment 2, and you'll measure the rate of that guy. So that's the method of initial rates, and it's pretty simple. If you've got, for every reactant, you need 2 experiments where its concentration is changing. Now, it's a little complicated, especially if you've got multiple reactants. You're going to have to do a large number of experiments. Now, there's an alternative approach, but it only works when you have 1 reactant, and that's called graphically determining the reaction order using the integrated rate laws. So what you do in this case is when your reaction has only 1 reactant is you do a series of plots. You do 3 plots, or however many you need, and you're going to plot like log of the concentration of your reactant against time. You're going to plot 1 on the concentration of your reactant against time, and you're going to plot the concentration of your reactant against time. And if your graph for the log plot is linear with a negative slope, then that tells you that it's first order. If your graph for 1 on the concentration against time has a positive slope and is linear, then that tells you that you're second order. And if your plot of concentration against time is linear with a negative slope, then that tells you that you are 0 order. Now, what's also cool is not only does this tell you the order of the reaction, but you can also get the rate constant because the slope is equal to, in this case, minus k. The slope is related to k. So what that means is by making these 3 plots of one single experiment, we get both the rate constant and the reaction order, which is really cool. So, that's kind of like a nice, simple kind of way of doing it. The problem is it only works for those reactions where we have one reactant, which conveniently is what we're going to study. So we're going to study a reaction where we have only one reactant, and we're going to study the catalytic decomposition of hydrogen peroxide. So hydrogen peroxide spontaneously decomposes to produce oxygen gas and liquid water, but it's like modestly slow. So when you buy an aqueous solution of hydrogen peroxide, it will come in a brown bottle often because preventing sunlight from hitting the hydrogen peroxide actually slows down the decomposition. Now, the decomposition of hydrogen peroxide aqueous solutions generally occurs over a period of weeks or months. So that's obviously too slow. So what we're going to do is we're going to put in place a platinum catalyst that'll kind of speed things up. And so then we're only going to need to study the reaction for 3 minutes in order to be able to figure out what the rate constant is and the reaction order. So the rate law for this reaction is going to be of the form like this. Rate is equal to K, and because we only have the one reactant H2O raised to some order, right? So A is the order of this reaction. Now, if you look here, you'll see that one of the products is a gas. So what that means is if we do this in a closed container, the pressure will go up. And the pressure will go up according to how much gas we make, right? Because we know that PV equals nRT. So if I measure how the pressure is going up, I'm going to be able to measure how the number of moles of my gaseous product, the number of moles of oxygen this reaction is producing per second, right? And then because I've got a balanced equation, I can figure out the number of moles of H2O2 that's being consumed per second, and I can figure out the number of moles of liquid water that is being made per second as well. So what I'm going to do is I'm going to do this reaction in a closed container. The pressure is going to go up because oxygen is going to be made. And then using the ideal gas law, I'm going to relate those changes in pressure to the changes in the number of moles of oxygen, right? And then I'm going to use mole ratios to get the rate at which hydrogen peroxide is being consumed. So I can do this for one experiment and use the method of integrated rate laws to determine K and the reaction order. And I can do this for 2 experiments with 2 different concentrations of hydrogen peroxide, and I can determine the rate of this reaction using the method of initial rates. So that's exactly what we're going to do. We're going to take 50 mils of hydrogen peroxide aqueous solution. We're going to also add in there a 1 centimeter cube platinum disc. So a piece of platinum, 1 centimeter cube is the same as 1 milliliter. And that's all going to go inside a test tube that has a total volume of 150 mils. And then I'm going to connect to that a pressure sensor, right? And that's going to monitor the change in pressure, which will be the increase in pressure as oxygen is produced. So oxygen is going to kind of be produced and fill up the space above the aqueous solution of hydrogen peroxide and the platinum disc. And what I'm going to do is I'm going to measure the pressure twice per minute. So that means every 30 seconds for 3 minutes, right? So I'm going to get 6 measurements, right? I'm going to do this for one concentration of H2O2, and then I'm going to do it for a second lower concentration of H2O2. And the whole thing is going to be thermostated at exactly 25 degrees Celsius or 298.15 K. So when I do that, I get this data, right? I get data where I'm getting a point every 30 seconds. So initially I zero out the pressure meter, I wait 30 seconds, and the pressure rises because I'm making oxygen, right? And so on for the whole 180 seconds or for the whole 3 minutes. Now I do this twice, one with a lower concentration, once with a higher concentration. And I'm going to be able to use the 2 different experiments and the method of initial rates. I can also just take data from one experiment and use integrated rate laws to find the reaction order and the rate constant. So let's have a look at the 7 questions that we're going to have to do. So the first question asks, are the differences in the 2 sets of data what you would expect? So let's go back up and have a look at the 2 sets of data. So one is at a higher concentration than the other. So we would expect that reaction, this guy over here, is going to run faster than this guy. And that's what we see at every time point. We have a greater pressure of O2 for the more concentrated hydrogen peroxide than we do for the one with the lower concentration. So that looks sensible to me. And if I was doing this experiment for real, that would be the first thing that I would look at. So I think that that's pretty easy to explain, that it looks about right. So the next question asks, what volume in liters will the oxygen produced occupy? So there's a couple of things here. We want to make sure that we give our final answer in liters, and we also, because we're giving a number, we want to make certain that we get our significant figures correct. So if you recall what the experiment is that we're going to take a tube that has a total volume of 150 milliliters. Now we're going to want to check the sig figs on that, and I believe it is how it's given is out to the 0.1s. We can check that right now. In fact, let's just let it linger. There we go. Placed into a cylinder. Yep, with 150.0 milliliters. Okay, that's good. We got that correct. So total volume is that. It's got an oxygen sensor or a pressure sensor that's sitting up there. And then we put in here 50 milliliters of the aqueous H2O2, and also we've got a platinum disc that occupies a volume of 1 milliliter. Now you can't have 2 things in the same place at once, so where is the oxygen going to be? The oxygen is going to be up here, isn't it? Above the liquid, right? It's going to bubble and be released into that space. So how much space is there for the oxygen? 150 minus 50 minus 1, and that is 99 milliliters. Now everything was given to the 0.1s, right? Everything was given to the 0.1s, so our answer should be given to the 0.1s as well. But we're not quite done because it wanted it in liters. So we've got to do 99.0 milliliters times, and we know we get 10 to the minus 3 liters for every 1 milliliter. So that means that this guy is going to be given to 3 significant figures, 0.0990 liters, right? Leading zeros never count. Trailing zeros count when your number has a decimal point. Non-zeros count. So there's my answer. So that's the amount of space that the oxygen can occupy above the liquid. So we're doing good. We got 1, 2 out of our 5 questions complete. Now it looks like we're going to have to fill in some big tables here, and that's where things, obviously we're going to start doing a significant amount of math at this point. So we just got to take our time. And the thing about tables is you're often repeating the same calculation again and again. You just want to read the instructions carefully and make sure you know what's going on. And I'll do one example calculation of each type. So it says complete the following tables. Okay, there's 2 of them, one for each concentration. Right, and what we've got is data of time versus the pressure, just like we had before in the first document. And the first thing that we have to calculate is the moles of O2 produced and the moles of H2O consumed. You're also asked to give an example calculation for each column, and obviously there isn't enough space here, so you'll do that on some additional sheets of paper. You're also asked to give your answer in scientific notation to 4 significant figures, so we need to be doing that. So at time 0, it's pretty simple. It's pretty obvious, hopefully, that no O2 is being produced and no H2O2 has been consumed. So we're not going to do our example calculation for that. We're just going to put a dash there, or perhaps we could put not applicable if you really wanted to. But that isn't, there's nothing to calculate for that guy. All right. Now what's going to happen is this. So as the reaction progresses for 30 seconds, some O2 will be produced. And how we're going to calculate how much O2 produced, we're going to use PV equals nRT, okay? Then once we've got the moles of O2 produced, we're going to use the mole ratio from our balanced chemical equation to calculate how many moles of H2O were consumed. And then what we can do is, once we've figured out how many moles of O2 were consumed, we can figure out what the remaining concentration of H2O2 is in our 50 milliliter sample. So let's go ahead and do an example of each of these 3 types of calculations. So the first one is to calculate the moles of O2 produced. So what we know is that PV equals nRT. So that means that PV on RT equals N. So our pressure in this case has to be given in atmospheres, and so at T equals 30 seconds, it was 90 torr. So we got 90 on 760, and that's going to be my pressure in ATM. My volume is just that volume above the liquid. We already calculated that in the previous question, 0.0990 liters. And then that all gets divided by R, 0.0821, or if you want, I think you can do 0.01. It's like 1. You could do this out to 4 significant figures, I guess is what I'm getting at if you really want to. And then 273.15, because it was at 25 degrees Celsius, is my temperature. I should put in, actually, let's repair this a little bit. I should put in the units for R. It is liters, atmosphere, per mole, per degree Kelvin. And then Kelvin was 298.15 Kelvin. There we go. So kelvins, kelvins, liters, liters, atmospheres, atmospheres. And then you're left with 1 over 1 on moles, which is 1 over 1 on something is just going to be the number back. So it's just going to be moles. There we go. Now, I would expect this to be a fairly small number of moles because we didn't have a lot of H2O2 to begin with. So let's see what we've got here. So we got 90 on 760 times 0.099. That's my top line. Divide parentheses 0.0821 times 2 98.15, close parentheses, and hit enter, and that's it. 4.789. Remember, we want 4 sig figs by 10 to the minus 4. 4.789 by 10 to the negative 4 moles of O2. Now, you remember our balanced equation. 2H2O gives me 2H2O, 2H2O2, and a mole of O2. So we're also asked to calculate the moles of H2O2 consumed. So what I've got here is 4.789 by 10 to the minus 4 moles of O2 times, from our balanced equation, we get 2 moles of H2O2 for every 1 mole of O2. So what do we got to do? We've got to multiply our answer by 2, right? And that'll give me my moles of H2O2. And again, we're going to do 4 sig figs and in scientific notation. So pretty simple. I'm just going to go times 2. So there we are. And then that's going to be 9.579 by 10 to the minus 4 moles. So that's how much was consumed, right, of the H2O2. So we're not quite done because we have to calculate the molarity of the H2O2 after 30 seconds. So how many moles of H2O2 did we have to begin with? Well, we had 50 mils or 0.0, or let's actually just do it this way, 50 milliliters. And the concentration in this first experiment here was 0.882 moles per liter. .882 moles of H2O2 for 1 liter, or another way of writing 1 liter would be for every 1,000 milliliters. You can see that that's going to work, isn't it? All right. So initially, I had 50 times 0.882. Oh, yeah, that's right. On 1,000. There we go. Initially, I had that many moles, 0.0441. 0.0441 moles. That's what I started with. And then I used up 9.579 by 10 to the minus 4. Minus 9.579 by 10 to the minus 4. That's how many moles I used up, right? So that means that what I've got left is minus 9.579 by 10 to the minus 4. There we go. I've got left 0.04314. 0.04314 moles remains. And that's going to be dissolved in 50 milliliters of water, right? So 50 by 10 to the minus 3 liters. Okay? So my new molarity of my hydrogen peroxide is going to be that divided by 50 by 10 to the minus 3. There we go. My new concentration of hydrogen peroxide is 0.862842, right? 0.862842. 862,842. Let's make sure we got it right. Moles per liter. And we have to give that to 4 significant figures in scientific notation. So it's going to be 8628 times 10 to the minus 1 molarity, right? So that's going to be my new molarity. So the molarity is going to go down. As we go down that table, it's going to get less and less and less and less, right? As we go down here, right? And this is just going to get less and less and less as we go down. Now, I've got to do that a bunch of times. I've got to do it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times. So it's quite a lot to do, right? So, just be aware of that this is not going to be a trivial thing to do. So now that we have our concentrations of hydrogen peroxide at every time point, we can go ahead and start calculating some rates for its decomposition. So the first thing that we're going to do is calculate the average rate between 0 and 3 minutes for each experiment. Now, 3 minutes is the total time for the whole experiment. So we're going to calculate two rates, one for the higher concentration, which will be faster, and then one for the lower concentration, which will be slower. You have to show all your work. You might need to attach additional pages, and then you have to give your answers in scientific notation to 4 significant figures, and of course they should have the correct units. So what is the rate going to be? What's the average rate going to be? Well, it's going to be the concentration of hydrogen peroxide at 3 minutes. Let's just make that rather than at time 2. We know that time 2 is going to be at 3 minutes. Minus the concentration of hydrogen peroxide at time equals 0 minutes. Want that all in parentheses. Now that'll be a negative number, unless we put a minus sign out the front. And then it's going to be 3 minutes, or if we want to express this in seconds, we could say, no, let's just do it in minutes. 3 minutes is our time 2, minus 0 minutes is our time 1. And so that'll give us that. Now we're going to do that for both of our reactions. And we would expect the one with the higher concentration of hydrogen peroxide to be undergoing a more rapid reaction and to have a greater rate. So you do that for both of your concentrations, and then the units here are going to be molarity per minute. Now, of course, if instead of using minutes, you could use seconds, it doesn't actually give you any, you could use either seconds or minutes for that. So remember that 3 minutes is 180 seconds if you're going to do that. Either or, it's your choice, but the important thing is scientific notation and 4 significant figures. So that's kind of getting better. Now, this is where it gets kind of interesting. It says you're going to assume that the average rate over the first 3 minutes is a good approximation for the initial rate. So really what we're saying is the hydrogen peroxide concentration is going to go down like that. The initial rate would be the slope right at t equals 0, but we're going to say that that can be approximated as the average rate, which is the slope of the line joining 0 and 3 minutes together, right? So we're going to use those two rates as an approximation of the initial rate for each of those two concentrations. And then it says use the method of initial rates to calculate the rate law and the rate constant. So the rate law is going to be of the form H2O2 raised to some power A. And how we're going to get A is we're going to do log of the rate in experiment 1, and that was the one with the higher concentration, wasn't it, over the rate in experiment 2 divided by the concentration of H2O2 in experiment 1, or the log, sorry, of the concentration of H2O2 in experiment 1 over the concentration of H2O2 in experiment 2. So once we've got our A by doing this, then we'll have the rate law. So the rates are just those two numbers that we calculated up here in question 4, and then the concentrations are just those two concentrations that were given in our table. So pretty easy to get what the order is, right? And so it should be either 0 order, first order, second order, something along that. It's going to be close to a whole number. Now, once you have the rate law, it's then going to be fairly quick to go ahead and calculate the rate constant. So all you have to do once you've got the rate law is reorganize the rate law to get the rate constant. So let's assume that we do all of this and we decide that it is 8th order. Now it's not going to be obviously 8th order in H2O2. So then we'll go rate divided by the concentration of H2O to the 8 equals K. All right, and we already got the rate in question number 4. Okay, so we've got 2 of them in fact. So if you want to, you can do this twice, but you only need to do it once. So I always suggest using the data from experiment 1. So we're just going to take the rate for experiment 1 and then divide that by the concentration of H2O2 in experiment 1 raised to whatever power we got up there for the first part. So 2-step process. One is use the method of initial rates to get the order of the reaction. Once you've got the order of the reaction, you reorganize your rate law and you solve for K. Now, something to be aware of is that you want to, you want to be cautious about your units for your K. And there's a table 12.2, I believe it is. I've got it highlighted in here that has the units for K depending on the order of the reaction. So if it's first order, your units for K are going to be time to the -1, seconds to the -1. If it's second order, they're going to be concentration to the -1 times to the -1. If it's 0 order, it'll be concentration multiplied by time to the -1. So you should be able to assign appropriate units for K, and I put the general formula for the units for K into the lecture notes, so you should have those available to you. All right, now the next bit is kind of the link between method of initial rates and integrated rate law. And what it's asking you to do is to create a plot for both experiments of log of the concentration against time, okay, and then to determine the slope of that plot. Now, what's the reason for doing that? Well, what you're really doing is you're kind of confirming that whether it is first order or some other order of the reaction. So what you're going to end up with is possibly a plot where you put log of the concentration of H2O2, which you already calculated up here, right? And you're going to do this for each set of data against time. Now, if your reaction is first order, that will be linear with a negative slope, and the slope will be equal to the negative of the rate constant, or alternatively, you can say that the negative of the slope is equal to K. So you calculate the slope between 2 points and it will give you K. You're going to do that for both of your experiments. Now, when we think about the properties of K, what we know is that it doesn't depend on anything other than the temperature. So even though we had a different initial concentrations of H2O2 for the 2 experiments, K should be the same. Furthermore, the K that we get using the integrated rate law for a first order process should be close to the K that we got when we used method of initial rates. Now, there's going to be some discrepancy, and you can probably imagine what the discrepancy is about. We made a pretty big assumption, right? Whenever you see that assume thing in your lab, you know that that's going to come back to bite you in the butt a little later on. And what we assumed was that the initial rate was the same as the average rate over 3 minutes. Now, is that strictly true? Something to think about, and I bet you they're going to ask you about that somewhere along the way. So you've got 2 graphs to make there. So what we are now asked is this: are your graphs consistent with the rate law and rate constant determined in 4? So in 4, what did you do? You used method of initial rates. But we approximated initial rate. So my guess would be, and I'm not going to do the whole lab for you because I'm already like 40 or almost 40 minutes into this video, is that these 2 rate constants, the one that we determine using the integrated rate law and the one that we determined using method of initial rates are going to be close, but not the same, right? That's what I would think. Yeah, that's what I would expect. Now, this is assuming, of course, that it really is first order. If you get a curve when you do the log against time, then you know that it is not first order. It must be either 0 or second order. So anyway, it's a pretty involved lab, and I would encourage you to get started on it as soon as you can. Yeah, and also just let me know if you have any questions, and please send me a draft before you submit your final work, because this has the potential to go really poorly for you. But it's also pretty good revision if you do, do allow enough time for completing it, and you seek help when you get stuck.